Okay, one more minute to finish up, and then we'll get started. Yeah.
Hello.
Hello.
I have a question.
Yes.
What do you envisage us doing with a project wiki?
So Project Wiki is to basically share internal comments documentation. You may want to use it to upload things like design diagrams for the system, testing plans, that sort of stuff. Now, if you want to use Google Docs instead, I'm fine with that.
Okay. Yeah, that's what we've been doing.
So I would say fine. Let me just think. I mean, Project Wiki may have a little bit more flexibility for keeping like a hierarchical structure than Google Docs. Because what?
You have the document link in that,
Right, exactly. And it's easy to set up a navigation menu and to sort of go around. So, you know, if you have a systematic structure, a wiki may be desirable. But if what you have basically is discrete documents, then Google Docs should be, I think, perfectly adequate. Yeah, sure. Okay. Okay, I'm happy to see the teams having used that time a bit. I recognize that there's a tutorial this afternoon which is set aside for team meetings, and that's useful. Sometimes you can use this earlier time to set the agenda, to establish quick check-ins, so you can use the time together in a focused way later this afternoon, etc. So. In any case, I'm really happy to see people using that time. Please get in the habit of doing that and get in the habit of getting here on time to do that. I don't like to see people sitting in isolation. I like to see, you know, the discussion going on. Okay, so I'd asked you to view a video on what topic for this time? Yeah, it was on testability, particularly, right? It was on the characteristics of a program that help enhance the capacity to test that program. And we'll be talking about that. But before diving into that and having a more free-form discussion, I wanted to hit a number of issues I consider pretty critical for basic understanding related to testing. And as time allows, we'll have a more fulsome discussion related to this issue of testability. I'm going to be going through this as I want pretty quickly because I want to get you a set of best practices and the gist of them in a distilled form. Every year I find myself grappling at the fact that there's too little time to really do justice to these things. So it's going to be a view from 30,000 feet, and what we're going to be doing is applying it this semester to your particular problems. So we're going to be going through today a couple issues, tracking of issues that arise in software projects. These may be defects, these may be performance concerns, they may be inconsistencies between the documentation and what the system actually does, or other aesthetic unpleasantries. They could be bugs. And we're going to be talking about them, monitoring bug counts, and a little bit about the traceability side and this notion of a test matrix. So part of the motivation for this first part of the talk is that software development gives rise to a tremendous amount of detailed workflow. And we're going to be concentrating this issue of defect reporting and tracking. But there's also quite a set of issues having to do with client change requests for many projects, notifications for updates that are required from other pieces of software that you're depending on, and requests for peer review associated with artifacts. There's also a lot of change that goes on from the dev team to the test team when internal updates are available, you know, when a new release of this component is finished or what have you. Fortunately, automated software that handles a lot of that workflow can really facilitate these issues. Now, this whole issue of tracking defects and tracking identified problems with software is one that organizations have been grappling with for years. This shows a graph from an article by Watts Humphreys, who's some of you may know is kind of the author of the personal software process and an advocate of good practices on the process side in software engineering. And this shows for NASA three projects that sent out probes into space, in some cases now in interstellar space for Voyager. And it shows the number of defects found per 1,000 lines of code over time for these things by weeks of testing here on the x-axis. And a couple of things may strike you about this graph. First of all, that this is a multi-year effort. I would highlight the fact that with about 52 weeks a year, we're talking out here on the far sides of this over 5 years of effort of testing against these systems. Secondly, you'll notice that the testing tends to reveal more defects early, and then there's a convex nature of the curve. It gets slower over time, diminishing returns. Why might that be? Can anyone posit one or two hypotheses for why these curves go up fairly quickly early on, and then, at least with these two, the green and the yellow, they flatten out? Why would that be?
Kind of get the low-hanging fruit out of the way.
Yeah. Yeah, the defects that are easy to find are the ones spotted first. It's a little bit like, for anyone who's taken geology related to petroleum exploration, the big oil fields were identified first. They're the ones easy to stick a borehole in the ground and to find it. The ones that are smaller or less accessible get found almost by definition later, in some cases by definition. So some of the early bugs get found early, and you're dealing with a code base that's more and more rigorous. But you'll also notice that things are sort of episodic. There's sometimes a little bit of a plateau and then a growth again. A little bit of a plateau and then a growth. Any idea why that would be? Yeah.
Occasionally the discovery of one bug may lead to further bugs out.
Exactly. That's often the result of learning. You say, oh man, we missed that. How did we miss that? And you realize, well, our tests weren't looking for these certain type of things. These tests were catching a whole lot of types of defects, but they were missing this class of defects. And so that allows you to sort of plow through to discover another whole set of these problems. Or it may be as prosaic as you discover this bug and that's linked into or depends on defects elsewhere or causes defects elsewhere as a ripple-through effect. In any case, we're talking years of effort and diminishing returns. Let's talk a little bit about the stages in the life of a reported defect. There are several salient stages that we're going to be delineating in the next few minutes. And these have very material implications for your projects. Perhaps the one with the deepest implications is this class of undiagnosed bugs. This is the one that it's hardest to assess, but arguably is the most important one. Why do I say that? Why would it be so important how many undiagnosed defects you have?
It's difficult to mitigate problems you're not aware of.
Yeah, exactly. It's difficult to deal with these because you don't know their character, you don't know how many of them there are, you don't know what they are. They're very little directly at the moment. They're a little under your control, and they can have a huge impact on the success of your software. So leaving this stock, as we'll call it, of undiagnosed bugs and going to the stage where they're actually diagnosed at some level, they're identified, is of absolute central importance in software. And I would note that because this is unobserved, because it's not directly observed, it's easy for us to fool ourselves about how big that is, to think there's almost nothing there where really it's huge. And getting beyond that uncertainty is one of the most important steps of testing, for example, and other aspects of quality assurance like peer review. So this stock of undiagnosed bugs is of great importance both because We don't know much about it. We can't directly act on it immediately. There's often delays involved in diagnosing these, and because it's easy for us to fool ourselves about it. It's easy enough for us to put on rose-colored glasses and think that that's very small. And then there's a set of stages: perceived possible bugs, actual distinct bugs, bugs that are actually delineated from each other, that are not just perceived as possible, not duplicates of each other, not outdated, but they're actually distinct bugs. Triage bugs, bugs that have been decided they're worth fixing, bugs that are assigned to different developers, bugs that are believed fixed but not yet closed by the reporter, and then fixed bugs, bugs that are resolved and eventually closed by the test team often, and marked as fully resolved. And then there's some later things like feedbacks from bugs. Bug fixes can sometimes introduce other defects. Can you believe that? Yeah. No way. Yeah. Right. You go and you fix X, and it's like squeezing a balloon. You squeeze it here, and it pops out there. Have you ever had that happen to you? I'm really torn. A part of me wants to say, I hope you've had it happen so you can understand this. If it's happened to you, I hope you notice it happening. But it's a painful experience, right? Oh, fix that. It's whack-a-mole day. And then bugs revealed by fixing other bugs. So let's put these in a sort of structure. This is called a stock and flow diagram. Those who have been in 394 will recognize this. But we've sort of mapped out this process here. So here are these undiagnosed bugs. Oh, man. Undiagnosed bugs over here on the left-hand side. And these bugs, through a process of testing or peer review or other aspects of quality assurance, go on and become bug reports. And then through a process of sanitization, they go on and become active bugs. I need you to understand these terms. Sanitization involves basically checking if these are truly a new distinct bug. So give me a reason why something that's reported as a bug may in fact not be a new distinct bug. And I should be recording the screencast of this, so pardon me, I'm just going to start that. So give me a reason why something that's a reported bug might not be a new distinct bug. Give me, yeah. Right. So it could be they're using an older version of your system, of your app, perhaps, which was had this defect in it, but it's been fixed since, right? And so they're reporting something that is passé. It's no longer of interest to those on the dev team because it's already been fixed. Give me another reason.
Part of a recognized problem?
Yeah, it's part of a recognized. It's a problem that's already been reported. It's this was reported 2 days ago by someone else, right? And those sorts of. And what's another reason? Anyone know? Sorry. Okay, there could have been a change in requirements, which now says, okay, that was a bug, now it's a feature. It could be, or it could be due to a misunderstanding, right? Someone reports this thinking that it's a problem, and it's actually by design, as it said. This is how it was actually supposed to be. Or it could be due to something that's technically not a bug per se with the system, but it's a misunderstanding or an inconsistency with the documentation, for example. So you have duplicates, you have outdated things based on poor understanding. So this sanitization process is extremely important for knowing, how many really real, distinct defects do we have? And those are what we call active bugs, okay? Now, not all of those bugs are necessarily going to be, not all of those defects are going to be, in fact, fixed. Why not? Why not fix all defects?
Some might be really integrated into your system and they're not actually that
Okay, they might be mild in their implications, and fixing them might do what?
Cause more bugs.
Might cause more bugs. It's a very real thing. And in fact, in commercial software projects, before you roll out or before you ship, if you have to fix a defect in the end game, really, really late, you're going to do so with a level of precision that's often associated with a surgeon. You're going to be wanting to study this problem extremely carefully. Why is that? Why do I say especially late in the game?
Might cause some side effect that would cause, like, a final build to have some bug that no one's ever seen.
Yes, and if it's really late in the game, that might not be discovered before you roll out, right? There's not the time to do another round of fixing. There's not the time to do another round of testing that's thorough. So if you're going to fix this thing now, you got to get it right, or you may cause problems which you're not going to have time to discover, and which could therefore bite the customer and cause egg all over your face at the least, cause a customer who goes to your competitors, or cause a customer who loses work or is otherwise delivered negative value. So this is a very serious issue, whether you decide to fix this. And in general, folks, there's limited effort available. Can you believe that? Can you believe that late in this term there'll be limited time to fix things? You bet. There'll be limited time, and so you've got to triage. You've got to figure, okay, what can we live with? What's maybe an annoyance? What's a disappointment? But fundamentally, we can live with it. And what things do we have to fix to roll out at the appointed time? So this triage process, which often involves discovering how many actually are in this area, this active bugs area, and then going through and rating them according to a standards we'll be talking about in a bit. That's a key process. So once you triage it, you decide, okay, these are bugs that are worth fixing. They're kind of important bugs we're going to focus on. And then you assign them to various devs. And the devs, hopefully, through the fullness of time, will try to fix these defects. And they'll be checking them in and reporting them as fixed at some point. Now, if the reporter of that defect ends up checking it and that defect is not fixed, it'll be kicked back to the developer or kicked back into the queue. And typically it's to the same developer. Why to the same developer, folks? Why would you do it to the same developer as did it before? Why is that important? Yeah, they need to know where they went wrong. They've thought it through, or they failed to think it through enough. But they're at least part of the way thinking it through, and hopefully they'll grok what happened and fix it. So you may kick a lot of these back to this stage, but if the reporter of it, and often this is someone in the test team or an end user, confirms that it's resolved, it'll be going to this resolved category. And sometimes there's a further process by which it's viewed as closed. Case closed, it's done, it's in the past. Now, is that the end game for the bug? Is that the end game for that defect? Not necessarily. It may come up again. And so you put in place what's called a regression test to test against this. You make sure that it won't, again, pop up as someone tries to fix another defect and reintroduces this one. Or as someone merges code bases. Could you imagine this happening? You merge versions of source code, and this old defect comes back. They didn't merge properly, and they end up reintroducing it. Yeah, it can really, really occur. So these things are very, very common. Now, this active group here, as I mentioned, often a lot of defects will stick there. If they're too risky to fix, risk is absolutely key. It's key because there's uncertainties and there's limited time. And you're not sure how effectively we can fix this thing, and it's a bridge too far, and you decide, let's leave this thing. It's the devil that we know. We'll leave it there, and we will work forward, and we'll document it. And that's what I'll be looking for in your documentation. I don't expect your system to be bug-free, but I sure want to see documentation of the defects that are in there. It may include some defects that are too minor to merit the cost to fix, or the defects you just don't have time to fix realistically. You punt them down the road till the next time. So what's going on here? You've got testers who are trying to discover things, and this can include end users in some cases. Can they reproduce the failure? Does it exhibit a problem with the system or merely with the test? Could you imagine a test might have a defect? Yeah. Yes, tests can have defects. Tests can have defects. Your test may be improperly putting the system through its paces. It may not be showing an error where there really is one, or it may be reporting an error where there's not one. And they're trying to figure out what factors influence the failure. Why might they do that? Why might these testers have to reason about, okay, what contributes to this?
Is it system or human error?
Yeah, okay, there could be a human error component. And also, to simplify the test case as far as possible, to make it really, really easy to reproduce. Make it sweet. You just do this, do that, boom, down. There's a certain joy that comes from that, I must say. And at that point, a bug report, once the tester has kind of explored it, figure out what things are really needed, what things are extraneous in terms of setting this up, getting it readily reproducible, they send off a bug report, and the developers are wondering, okay, what's the root cause of this? How can I repair it without introducing real problems? Is my fix going to introduce issues? And then, the testers end up eating the products of that. They see a check-in. The check-in occurs to subversion. It's marked as an attempted fix of this bug. And they're informed, okay, this should be resolved in this latest version, this latest release. They could see from the issue tracking system like Jira or Redmine, they see that it's reported as fixed. And so they're going to be checking, is it really fixed? Does the system now pass this test, which previously failed? And does the rest of the system still behave properly? Right? Does this make sense to you as a process? Okay. So what are in these defect reports that are in Redmine or Jira or Track or name your system? Well, often a brief title, a priority associated with this, and a severity. Now, I need to delineate those two things strongly for you. Priority versus severity. Priority includes consideration of severity, but a set of additional factors. Severity has to do with how bad this thing is if it occurs. Conditional on it occurring, how severe is the damage caused by it? Now, a terrible type of bug might cause a crash, right? System fails. Is that the worst thing that can happen? No. What's worse than that? Data corruption, destruction of the data, and delivery of negative value. I mean, crashing is bad. You haven't been able to achieve what the user wanted, but destroying what the user's assets is considerably worse. Of course, what's even worse is data corruption that doesn't go noticed. The system continues to run, silent but deadly, helping them, they think, to make terrible decisions. Another issue, though, is priority altogether. So severity is conditional on occurring. Priority considers not just the severity, but also the probability of its occurrence. We talked earlier about a similar distinction in what context? In the issue of risk management, of doing effective risk management, where you have to consider the severity of something if it occurs, but also the probability it occurs. And we had this notion of risk exposure, remember that? Where you have severity times priority, probability of occurrence times the badness, or maybe that's rated on a scale of 1 to 10 or what have you, 0 to 10. Priority here fundamentally boils down to, how important is this thing to fix? Must fix if possible, desirable. entirely probable. That's one set of distinctions. I don't actually like these ones that much, but you know, it gives some measure of, okay, what level of overall need is there to fix this. Another thing that's part of this bug report is a reproduction formula. Person assigned to. That might initially be blank, but the test team might say, okay, that's assigned, or excuse me, the dev team says that's assigned to so-and-so. The test team often won't be able to directly assign it. They don't know who worked on what directly in some cases. What are the projects? Who opened it? Why might you want to report that? No, it's not for the dev to get mad at that person. Yeah, they want to know, you know, hey, look, I haven't been able to do this on my tablet. You're saying you found it. What were you using as the device? What, you know, under what conditions? Can I see it? Can you come over and help me reproduce it on my tablet, right? What's the status of the bug? Is it active? Is it fixed? Is it resolved or closed? Where, again, resolved is kind of this intermediate state. The fixed is the developer says it's fixed. Resolved, the reporter agrees it seems to be resolved. Closed, test team says this is done. This is history now, and we'll view it as a closed defect. Maybe it also means that it's incorporated in the regression test suite. And you know what type of bug this is? Is this a regular bug or is it a regression? Is it actually something which is coming back up that failed, that was a previous defect and it's re-emerging, for example? And is this triaged? You know, is it rejected as a bug? Is it treated as, okay, we don't have time for this? Okay. Now, creating a defect report of this sort is a bit of an art. It requires structured exploration, trying to reproduce it, test that several times, trying to isolate it, and figure out sort of whether there's underlying rules for this. Did this occur in an earlier version? Did this occur last week? You just didn't notice? You weren't thinking to test this? That can be really useful. Why could that be useful?
Figure out whether one of our recent changes put in place or whether it's further down the line.
Yeah, exactly. I mean, it can be really good to know if this is new as of this release and it wasn't there last week, even though the features involved were there, that may be a real indication about what might have caused it. Maybe that's not something that the tester is going to directly benefit from in their work, but it's something the dev might find really, really helpful, the dev who's assigned it. You know, summarize it, condense it, disambiguate it, neutralize it. What do you mean by neutralize it? We're going to neutralize the report. Doesn't mean we're going to add, you know, base and acid. Basically, it means that, look, this is an age-old issue. Developers can get a little bit sensitive at times, particularly if they're working very long hours, if they're under stress, and if they feel their work's very good quality, they're very proud of it, they can grow defensive at times about their work products. And it's one of the challenges of being a tester that you have to navigate this human theater associated with people's sensitivities. Yes, you are helping the developers to create a better product, but you are doing so by pointing out problems. And you can do so in a way that's more careful, more circumspect, and less likely to be taken personally, or you can do so in a way that is likely to trigger an adverse reaction. And this is an age-old, well, computer age-old issue that bedevils projects. And in this class, we've had teams that grow apart from each other, developers and testers. And I can't say with certainty how much this particular component contributed to it, but it can be a notable factor in sort of getting the developers thinking the testers are just always on their case. Well, guess what, folks? Testers will not be on your case if you're putting out code which is higher quality. They'll be less on your case. But their job is to spot issues, and you should view them as part of the team. It's just if you can avoid gratuitously upsetting the developers by phrasing it carefully, it'll be in your interest to do so. Do you agree? Yes. Can you imagine a developer who might get a bit irked by saying, like, another one of your stupid bugs in this feature which never worked anyway? I mean, it can irritate people, and it can do so unnecessarily. I mean, why throw gasoline on a fire, right? So this is going to be painful enough to get yet another bug at 11:30 p.m., 2 days before the deliverable, another bug report. Just try to do so in a way that's a little bit more circumspect, okay? And then review it. Okay, so let's talk about reproducing bugs. An art form. Okay, a very important principle here is reproducibility. And one component of that is to make a copy of data that can be destroyed or modified before the test. Why do I say that's important for reproducibility? Well, if the test is depending on some initial state, maybe you reproduce at that time, but how are you going to reproduce it again if you can't recover that initial state? So you make a copy of it so that you can easily get back to the state if you are successful in getting it to be the bug to be triggered, or the failure to be triggered. Ladies and gentlemen, in this course, and this is an important distinction, and somewhere I'll have a slide which formally introduces this, but let's talk about the distinction between a failure and a fault. I'll use those terms advisedly. I'll use them carefully. What do I mean by a failure? I'm talking here about an observable symptom that indicates a divergence between what the program does and what its requirements, either direct requirements or derived requirements from those, tell it to do. Between how the program should be and how it actually is in terms of its observed behavior. This has to do with the observed behavior, the failures. Okay, so the failures are observed. What are the faults? Yeah, they're the things that are often not directly observed. They're the underlying problems that lead to a failure. Can a given fault lead to multiple failures? Yeah. Could a failure be caused by the interaction of multiple faults? Sure.
Faults could also not cause failures, right?
Faults could, in some cases, not cause failures. There's a problem that's latent in the system, but it's not being reached right now. The code is not going on those paths in any of the tests you're running. But guess what? The end user might reach that latent defect. So, but moreover, given the spec of the system right now, it may be that logically there's a fault. There's something that you didn't realize, and it's just within the range of how the system's going to be used right now. It's not a problem. But when you start to expand the system, it will be revealed. So we distinguish between faults and failures. And here we're trying to observe the failures. We're trying to observe these symptoms. Now, if you're doing exploratory testing, those of you who will be doing manual testing against the system, and I think they'll be going on quite a lot, it's a very important component of testing, I would suggest strongly that you jot down roughly what you're doing. What are the steps you're going through? Or record it if you can. This can allow easier reproduction of bugs. You don't want to be in a situation and say, what did I do? What was I doing? What were the steps that led up to this? You want to be able to easily recreate it. So what are some steps associated with this? Whoa, man, I don't know what's going on. My computer doesn't seem to be falling asleep or anything, but this thing is... Huh? Is that right?
I think it was happening during the meeting we had too. Could be from the computer. That was something else.
Okay. That's. So you think it's stochastic flakiness? So it would appear.
Some sort of hardware thing. Either the port is broken
Yeah, it's exhibiting high frequency disruption. Okay. The interesting thing is it exhibits also correlation with mouse movement. So in any case, steps in. So I thought. Okay. Okay. Wow. The frequency is rising over time as well.
Do you have a display port on it?
No, I have just a full HDMI connection. Oh yeah, sorry. Thanks much. I wonder if something's heating up. Okay, so here we're going to prepare the system, prepare test procedures, execute them, evaluate the response, restore the test environment, and get it back to its original state. So what are some problems with reproduction? There's many issues that will prevent you from accurately reproducing a failure. And I'll share two stories with you. One story came from our own work, and this is one where a member of the class was actually involved. And we had clients who were using a system that we had produced, and were reliably complaining about certain inappropriate behavior by the system. The system was behaving in ways that were outside of our experience. We could not reproduce this problem. And we tried. I was involved in pushing it through a bunch of paces, and we could not get our system to reproduce this problem, and we would release new versions of it thinking that it was passed, that it was due to some defect that had been fixed, and they would report the same thing again and again. This is with a mobile device. And we were almost despairing about, okay, what is it? Could it be something, the fact they're in a different geographical area, of a different carrier for their phones? There's some sort of interaction with the local environment. Apps that were put on the phone by Verizon or the carrier. And it turns out it was very, very simple. And I want to highlight this, folks, because it's symptomatic of a broad class of problems with reproduction. The problem was that I and the others involved in testing it were testing it as a computer scientist would, with knowledge of what is proper and improper behavior. And so we knew that our system, as soon as you turned on the phone, it would start up by itself. So there were some icons for our system, but we would never touch them. Why? Why would you touch that? I mean, it's running already. And so we would never use those things. Always, we'd be testing it up, and we'd turn the phone on and then start testing it, and we did this again and again and again, couldn't reproduce it. And then I thought one day, there's an icon there. There's an icon for our system. Why don't I push that and see what happens? Particularly quickly after booting it. Boom. Saw the problem. And you could do it again and again. If you use that icon, it will cause the problem. And so we told them, and I think it was confusing to them. We told them, don't use the icon. And people are confused, like, okay, so why is an icon there if you don't want us to use it? Why do you actually present it? And so we ended up eliminating it through. It was fine. Yeah, exactly. So the issue is that often we test it sympathetically. That's an example of sympathetic testing. It's not that I didn't want it to reproduce the failure deep down. It's just that I knew sort of what was legitimate behavior, what would cause problems, and I just implicitly incorporated it in my repertoire. And so did others involved in testing. And so we weren't getting to the heart of the matter. There's an elephant in the room, and we weren't pointing at the elephant because we knew, well, why would you want to get involved with that elephant? So that's one example. I'll tell you another example that's of a different sort. So there's a lot of things where we, as experts, as computer scientists or as developers, we test it in a way that's very different from how users use it. And keep that in mind. If you have too much hubris, you may discover that you're not really testing it the way end users will. So getting in people who are not developers, maybe they're family, maybe they're friends of yours outside of the development area, to test this thing. People are totally unfamiliar with the system. It can be really valuable. That's lesson one. Lesson one. Lesson two. Ladies and gentlemen, we live in an analog world. So there was another faculty member here on campus who, like me, did consulting. And one of the places he went to consult was Wanaskewin. How many of you have been to Wanaskewin before? Yeah, okay, a lot of you. Now, Wanaskewin has gone through renovations over the years, but at least as of a couple of years ago, they had kind of a set of buffalo hides on a sort of wigwam type. It was sort of this little structure they'd cover with buffalo hides. Have you seen that? Yeah. And right next to it, they actually had a game. At least when I was there, it was called Buffalo Hunt. Anyone see the Buffalo Hunt game? This is inside. It was in this little room where they have artifacts displayed, from stone tools. There was a coyote, taxidermied coyote there. There was things that illustrated, how they processed food, etc. in old times. And one of the things, kind of the highlight of the room was this structure, which was covered by hides. This was kind of a pre-teepee teepee. It was before canvas, etc. And it was covered by buffalo hides. Do you remember that? Some of you? Okay. So this guy was part of the company that delivered Buffalo Hunt. It was this game where you could go and you could choose to hunt buffalo via different strategies, and it would sort of play you through various scenarios. And so they deployed this game after a lot of development and iteration with Wanaskewin. People seemed very happy with it, and they deployed it in Wanaskewin. And got launched. They were there, and they saw people playing. Everything seemed to be going great. They went back and patted themselves on the back and thought, okay, great contract. Now let's on to the next contract. And then guess what? They get a phone call. There's something wrong with the game. Something wrong with the game. It isn't working properly now. What's going on? Well, it's frozen. It's frozen. So what do we do? Well, they said, well, let's do something strange. Just reboot the computer. So they rebooted it. And they said, oh, yeah, it works great now. Okay. The Mac must have frozen up. Right? And so then, a couple hours later, get another call. Game stopped working again. Froze again. Well, okay, reboot it. So this went on, and it went on for weeks. And they would go over there and futz with it. They swapped out the Mac, I think, that was running it. Maybe it's a hardware problem. And still wouldn't work. Still wouldn't work. I studied the code. Nothing was obviously wrong. And make a long story short, I think it went on for weeks, and I think weeks became months. And Wanaskewin was becoming very concerned, because this thing would die maybe 3 times a day. The system would crash. And they almost despaired of figuring out what the problem was. But they decided, okay, finally, let's bite the bullet, and let's go sit next to this dumb game and watch it and just see what's going on. Like, is the user doing something strange? Is every user putting their mouse into the corner in just the right way to crash it? Or what's going on? So they went there and they sat for hours and hours and hours watching people interact with this game. And within a day, they knew what the problem was. So, person after person, they'd be going, it would play fine. And then a person would come along, and they'd be exploring the room too, and they'd go over to this little structure and say, wow, what buffalo hides? And they'd be patting the buffalo hides, and they'd go, oh, there's a game. And then they'd go over there, and guess what? It's winter, and there was static electricity. And boom, the game would freeze out. It was because of this. They put it on an anti-static mat, no more calls. That was it. That's an example of how an adverse environment can lead to problems reproducing things.
Not a single person, like, I just shocked this computer and it stopped working. Like, nobody figured out maybe that's the problem.
Nobody mentioned it.
Nobody walked over and was like, ow, or now the computer's broken. The owner, like, oh, it's totally just completely unrelated.
The thing is that the owners weren't playing it. Probably.
Yeah, no, the owners weren't playing it. They were.
No, like, even random people, like, would you not call over to somebody at the desk and like, I just broke this, like, this just happened?
Well, but they probably did. They probably said, well, it's not working anymore. But
well, it's like if there's a kid and he breaks the machine and he doesn't be guilty, he just casually walks away. Another person walks in, it's like, oh, this machine doesn't work. Why
yeah, static is not obvious to most people immediately as a cause. But
kind of the point, though, that people are not project managing, testing people.
That's right.
Doing their thing.
They're just doing their thing. They're trying to get on with their life, and a little static thing is like nothing significant in their life, in their world. I mean, what does it have to do with the computer? Static? Are you kidding me?
Let's think for a second.
So.
What does lightning have to do with managing a computer?
Yeah, well, suffice it to say that you'll find that users are a lot more diverse group than you would ever realize. So there's many other sort of more prosaic reasons, though, you might not be able to reproduce this thing. Race conditions? Anyone? What's a race condition?
When you have multi-threading and it's, your bugs are based on whether or not something happens first or second.
Yeah, that's right. It could be multi-threading. In general, concurrency. You could have multiple processes that exhibit race conditions as well. But you have two things going on at the same time, and it's dependent on the ordering or how quickly that one occurs after the other. If one occurs right after the other and something should be atomic and it's not, maybe the A occurs first and it starts updating some data structures, and B comes along and reads them while it's halfway through updating them, bad things will happen. That's why we want atomicity. That's why we want the acid properties, atomic, consistent, independent, and durable, that we seek within database context. External details that are forgotten and neglected. In some cases include static in the environment. External memory available in the system. Did something unintended and forgot. You actually reproduce this problem, but there was a step you undertook that you thought was so insignificant that it wasn't noticed. The bug changes the state. The occurrence of the bug changes the state of the system, so you can't then reproduce it. It writes something out in a way that's not reproducible. I had some professional development colleagues in Massachusetts who claimed that that the Windows registry was subject to being modified without detection, and so the first time this thing would occur, and the registry was secretly modified even though you could not detect it, and as a result you couldn't reproduce it again. So you would have to reinstall Windows or something like that from the start to reproduce a certain problem. Certain fragmentation of the heap. The heap is in a certain state. What sort of languages would this be an issue with more? Less so. C is really the issue, where you have dangling pointers, and what's going on in the heap is that there's certain structures in place, and maybe you're writing over yours, and sometimes you're writing onto this later structure, which, if it's located close enough to this one, you clobber, because you have this pointer which is searching for a null when it's doing some sort of string-related operation. It's searching for a 0 byte. So you can have situations where the relative placement of things in the heap will cause problems. Java is less bad for that. You can get issues where a garbage collection is, for example, triggered at certain times, and therefore the system becomes very slow due to heap fragmentation. Only occurs first time that your system runs, because it then overwrites some file on disk or what have you in a way that prevents it. a cascading failure. One thing leads to the other, leads to the other. So sometimes you see this, but it was only because of a silent error that occurred earlier. Time dependence, it occurs something to do with the time of day. So I have VirtualBox running on my machine. When I have to run Windows, I run it under VirtualBox. And all I'll say is that about once an hour, Windows crashes. And I'm trying to figure out why, but I think it's something with time dependence. Resource dependence is depending on some resource. And if the network's congested, if the disk is getting full, if there's some SD card it depends on the device, and it's over a certain limit, you won't be able to reproduce it. This can prevent easy reproduction of a problem. And last recourse for software engineers, hardware. Let's talk about test reports. I alluded to these earlier, and I won't go into them in much detail, but I want to ask you a question. And those who have taken 394, you can hold your tongues on this one. Okay, folks. So suppose week by week by week, we have some number of bugs that are found here, shown in blue with the diamonds. So some number of new defects that are reported, and some number, say these are triage defects, so they're reported to the level we're going to fix them, and some number fixed, shown in the sort of, I don't know what it is, pink, magenta? I don't know what that is. This lighter color at the bottom initially, which are the number of fixed per week. When is the number of defects in the system at the highest level? So this is the number of defects found this in week 1 and the number of defects fixed in week 1. When is the number the highest? Sorry? Open defects? Yeah, when is the number of open defects the highest?
Before the bugs found and bugs fixed overlap.
Yeah, so it's right here. As long as bugs found exceeds bugs fixed, the number of defects week by week by week is going up. Each successive week, you've got more coming in that are fixed. It's really the gap between the two that indicates the next. So in week 1, you have a net gain of how many? Of 100, etc. Right? So the number is going up. There's a net gain that's positive all the way up till they'll equal, right? And then a net decrease. And this is generally what happens with projects. That initially, the number of bugs found exceeds the number of bugs fixed. It actually doesn't go quite so linear. You actually get a ramp up as the testing infrastructure gets going. But initially, fixed typically exceeds, found exceeds fixed. And then later on, hopefully, the number fixed exceeds the number found. And it ends up declining. But the net upshot is that you see a real increase in the number of bugs in the system, sort of mid-stride here. And you'll see this project after project after project. And as I say, what's not represented in this graph is kind of a warm-up time as testing gets going and you get better and better at finding bugs. So directed triage, this process involves deliberately wading through this process to figure out, okay, which of these bugs are worth fixing, what's their severity and their priority. We talked about that earlier, but now that we have these notions of severity and priority, that's often involved. And figuring out, for those that are not yet sanitizing them to figure out, is this really a new defect? Is it a new and significant defect, or is it something that's outdated or a duplicate? So directed triage involves prioritizing, attaching priorities to bugs and sanitizing them as well. Okay, and if you wade through this process periodically, particularly as you approach later stages of a deliverable, it can reduce your uncertainty about where we're at. Yes, Kurt.
Is there someone in the group who's typically responsible for doing this, or some
Yes.
team that's responsible for doing this?
Yeah. So it's often project manager, dev lead, team lead, who are going to be taking responsibility. Why those groups? Well, testers will often have a really good sense of where the system's soft, where it really needs improvement, what's going to fly with end users. Testers, ladies and gentlemen, are the first power users of your system. They're the ones who gain some flavor of user experience. And they're the ones who are going to be able to tell you, you're fooling yourself if you think people are going to use this in its current state. They're the ones who are going to tell, tell truth to the hard truths to those in power, the project manager and the devs who are often eager to ship this thing. The dev team is going to be able to talk about how hard it will be to fix things, what will be safe, and they're going to be able to have comments about whether a given bug was fixed in the past, etc. And what recent versions came out that might have fixed things, be able to contribute to the discussion of whether something's outdated. And the project manager often has the best sense of the client and what the client is comfortable with. Okay, let's talk about a test status report. So, there might be a feature here. There's a certain number of tests against it, what number are complete, and the number of those that are successful of those tests. So having some sort of indication of what you're testing, and then some of these indications here of sort of what number of test steps have completed, or the % of tests that are complete that indicate success can be quite valuable. Let's talk about traceability, though. This is something I really want you to feature on your systems. The motivation for this is things change. I've told you before, a lot of the motivation for software engineering practices and processes are things change. And one of the implications of requirements changing, for example, or designs changing, is that they impact things downstream. What do we mean by downstream? So suppose a requirements document changes, or the requirements from the user changes. What could that impact in your system? Surely the requirements document, but what else?
Everything that results from it.
Yeah. So it could impact the design of the system in terms of kind of the architecture and how the different modules will work together, the APIs in place for each module, the interfaces they expose. All those things could be affected, and so could the code, right? A change in requirements ripples through to be changes to lots and lots of components. A change in design can impact downstream things like code, and both of those types of things can impact test cases. So the problem is, when we have these systems, there's a lot of dependencies that go unrecognized explicitly unless we take care to kind of link things up. So items are related to each other in structured ways that, unless you take care to note these things, they may go unnoticed. So for example, certain design components depend on certain requirements. There's a reason we designed the interaction of these classes this way, because we needed to capture these requirements. Certain code is written that relates to certain design components and that's designed, again, to meet certain requirements. Certain test cases are in place because certain code needs to be tested against certain requirements, for example. So for all these reasons, you get these interlinkages. And if you have a change to requirements, it ripples through. If you have a change to design, it ripples through. So let's talk about this thing that I want you to deliver on to me. And this is a very useful construct for thinking through testing in your system. Here, on the x-axis, we have test cases. On the y-axis, you'll have variously features, aspects of other functionality, requirements. And the test matrix basically allows you to figure out what tests are associated with which requirements or which features. Basically, if a feature here has an empty row, what does that suggest to you? Yeah, there's no test in place to test that feature. Could that be a problem? Yeah. So a test matrix is a great way to kind of look at your system, big picture, and figure out where are the gaps testing-wise. What things are we missing? What things here, could slip through the cracks? Well, feature 2 could be all messed up, and we wouldn't know it right now. none of these tests currently tested, right? So we need a test matrix like this to often recognize the gaps. You'll notice also, though, that certain test cases will test more than one feature. Why could that be? Give me an example of how a test might test more than one feature of your system.
For example, what the feature should test the login system if your system needs to log in because it's not running a page.
Totally, exactly. So it's a great example, Warren. So you know, an end-to-end test, a system-wide test will often first log in, and then it will go and see the user pursue some use case, right? They go and they undertake this, they undertake that, and they finish up by doing this final thing. So they go into the system, they want to form a new restaurant report, they select the restaurant from a list of restaurants, and they go and fill out the report, and then they save it. So that would involve testing several different features of your system. So ladies and gentlemen, I will want you, as part of your deliverables within your system, to give me test matrices for your system. It will help me understand what's being tested by what, and allow me to look at what exact features are being tested. Yes, Kurt?
Are you going to be putting use case tests on here as well as really specific, I'm testing this little specific piece of code?
Right.
Test that would all go on this matrix?
So it wouldn't necessarily go on a single matrix, but you might have one matrix that's high-level tests, testing against requirements features, and there might be a separate matrix that's geared towards more module level or unit tests or what have you. Because you could create test cases up here, and you could have specific functions down here, or methods of your classes, right? And say which test tests which methods, right? Or you could have down on the left axis interactions between one class and another. Which of those interactions are tested by which test cases to look at integration testing. A test matrix is one of those high-level structures that can be reapplied at multiple levels. And I wouldn't put it all into one test matrix. Rather, I would have probably different test matrices for different levels of detail. And incidentally, Kurt, what the set of test cases here at the top will be quite different. You'll have, in some cases, unit tests up here, and things that are focused of unit tests. In other cases, the test cases along the top will be system-wide tests, and you'll have features and requirements. So, great question. Other questions on this? Can you imagine creating this? Nothing too horrendous. And you'll see that there's another construct we'll be talking about, namely depicting your system as kind of a network, as a graph where you can move from state to state to state, which will also be able to be applied at multiple levels. So, these gaps, identifying these gaps should be the focus of a lot of your attention. And that's one of the things I'll be looking for. Where are the gaps in your testing? And I'll be checking some of your tests and seeing, okay, you report a test of this feature or this requirement. What is it you're really testing? Okay. Okay, now I asked you to review some material on testability. We don't have too much time to talk about it, but I want to discuss. Tell me some things that will enhance the testability of your systems. Okay, test hooks. Give me an example of a test hook.
Let's say you want to test network communication between two modules.
Yeah.
Then maybe the test team would ask the dev team to sort of output the state of connection at any given time.
Great.
Based on a specific method request or something.
That's right. Or, to flip that around, for those who have taken 332, this would be particularly familiar, the idea of a test hook in the form of putting in place a callback. So you insert, this would be done in a different way in Java. You don't pass in a function pointer. You pass in an object that matches some interface. And when a connection is established, it will call off to notify, hey, a connection has been established. And that connection establishment then might trigger some testing code that will save away the fact that a test connection was made at that time. So yeah, you might have a method which is exposed through a testing interface, not the normal interface, but a testing interface that basically allows you to peer inside and say, what's the current state of this? How many records are in your database? What was the last time you connected? What was the last record number that you uploaded? And it might allow you to do something like, look, okay, is this record number, is there any overlap between the record numbers that have been uploaded to the server and those still on the phone, for example? Because you don't want a record to be halfway uploaded and considered uploaded by the server and the phone to have it also in memory. You either want it totally uploaded or not uploaded at all, atomic. Okay, so that's a good example of a test loop. Give me another thing that increases testability.
Throwing exceptions, hitting assertions when things go wrong to
Yeah.
going on.
Yeah, assertions are great. Assertions are a tester's friend. Assertions are a test team's friend. Man, if they can get it, can push the system, and then it will trigger things when indicating its illegal internal state, that helps you zero in the faults much quicker. Imagine if the assertions help you spot the faults much more quickly, because they're often closer to the faults. If you have to wait for it to ripple through to another type of failure, other than an assertion failure, often it will take some time before it's manifested in the system crashing, or the system throwing up a dialog box, or an exception being triggered. Often the assertions will be much closer to where the actual problem first occurred. And so it makes debugging much easier. Do you folks grok that? Grok or not? Grok. I hope some of you grok it. Because you litter your code with assertions. You'll probably detect the problem much sooner than you would if you just relied on normal processing triggering something going wrong. You're putting in all these extra checks, after all. Let's talk about some other components. Good documentation. Why can good documentation help testability of your system?
The system makes more sense.
Yeah, and also you know what you're testing it against. You know against what you are testing it. Because that is the type of English up with which I will not put. Right? Yes, Warren.
It might also be the fact that maybe a precondition isn't being met, or maybe you're assuming that there might be a precondition where there isn't.
That's right. And as such, specifications are really helpful. If you can say what are the preconditions for this method or preconditions for this algorithm to be invoked, and you can test those in your assertions, those will often spot much sooner the fact that, hey, it's not the result of the algorithm that's bad. It's something going on before the algorithm, right? So you can test preconditions, postconditions, invariants, and history properties that we'll be talking about in this class to good effect by, if you're explicit in specifying them, and that's part of good documentation, is specifying those things.